Welcome. In today's video, we are going to derive the mean and variance of the negative binomial distribution. But to begin with, let us first define the PMF. So we say that if x is distributed with a negative binomial distribution with parameters r and p, where r is the number of successes and p is the probability of success, then the PMF of x, the PMF of x is given by where, and of course x represents the number of failures before r successes. The PMF is given by the following. Px of x is equal to x plus r minus 1, r minus 1, p to the power of r, 1 minus p to the power of x, where of course x can take values of 0, 1, 2, all the way to infinity. To derive the expectation or the mean of x, I am actually going to instead derive a similar related variable, but one that we can actually use more broadly to derive the mean, the variance, and other moments of x. So instead of just going straight for it, expected value of x, instead I'm actually going to derive the expected value of the following expression. The expected value of x choose k. So in other words, the combinatorial factor involving the random variable x when you're choosing k from x. And you might be thinking this is going to be a more complicated expression, and there will be some algebra involved here, but I want to assure you that we will be able to derive the mean and the variance using this expression. So without further ado, let's begin. So we know by definition that the expectation of a function for a discrete random variable is the sum across the whole support of x of the expression times the probability mass function. Now, one thing to note here is that we're taking x choose k. So while the support of x might be from 0, 1, 2, 3, 4, if we're going to be choosing k objects from x, at a minimum, we need to have that the first part of this terminal is equal to x, because before x, we can't choose, say, 8 objects from only 3 objects. Hence why we need to just specify that terminal. Instead of going from 0, it'll actually go above. So keeping that in mind, we've still got our x choose k, and we're going to substitute in our expression for the PMF. Copy that across, paste it down there. The next part of this simplification, what we're going to do is we're going to again rewrite the terminal, but we're going to express the two combinatorial factors in their expanded form. So remember, by definition, x choose k would be x factorial k over k factorial x minus k factorial, and that's that particular expression there, times the second combinatorial factor will be x plus r minus 1 factorial over, we've got our r minus 1 factorial from the bottom part, and then our final term here will be the top term minus the bottom term, and you'll notice that when you take the top term minus the bottom term, you're just left with x, so that becomes x factorial, and we've got the p to the power of r still, and the 1 minus p to the power of x. Now, one thing that might have stood out to you here is that the x factorial at the top of this numerator and the x factorial at the bottom of this numerator cancel out. And that is going to be a nice result that's going to help us do some simplifications. So we've got x to the infinity, and then we're going to rewrite this as x plus r minus 1 all factorial all over k factorial x minus k factorial, and then r minus 1 factorial p to the r 1 minus p to the x. Now, one thing that I'm going to do here, and one of the common themes when we're dealing with discrete distributions and we're trying to come up with an expression for their means and their variances, is typically what we want to do is we want to manipulate the summation, what is in the summation, to make it look more like a probability mass function. And the reason we do that is because when we sum across a probability mass function, we know that it goes to 1 by its definition. So that's one of the key techniques in the algebraic manipulation that I'm about to do. And there's one thing that's semi-standing out here. And what I want to do, recall, is I want to make this expression look like a, let's say, a PMF. So here we've got in the original PMF, if we just focus our attention on there for a second, notice that we have an x factorial down the bottom. Now down the bottom we have an x minus k factorial. So what I'm going to do very cleverly is I'm going to define a variable, and I'm just going to call it y is equal to x minus k on the side here. And then I'm going to substitute that all throughout the summation. That way, at least we're going to start seeing the remnants of the PMF. And let's see how far we get. So let's do that now. So we've got, sorry, I don't know why that terminal said k is equal to k. It should be x is equal to k. Now, if y is equal to x minus k, then when x is equal to k, y is simply equal to 0, and when x is equal to infinity, y is, well, still equal to infinity. Here in this expression here, we're going to put, we're going to substitute our formula. So x now becomes y plus k plus r minus 1 factorial. Close that bracket. K factorial stays the same. Now we've got y factorial r minus 1 factorial p to the power of r 1 minus p to the y plus k. Okay, so we're getting somewhere here. We are definitely getting somewhere here. Now what I want us to notice is another interesting point to get. Again, we're trying to get to a PMF. So in the original PMF, again, recall we had x plus r minus 1. Now at the top, instead we have a y, but we have a k plus r in its place. So if we have a k plus r in its place, instead of having a p to the r here as we have normally, what I really want to be able to see is a p to the r plus k out the front. Now that's actually quite simple to do, the p to the r plus k. The reason that it's simple to do is because, well, I originally had p to the r. Here it's still there. I've got a p to the k out the front. So now I just need to divide by 1 on p to the k all outside the summation to give me back the result that I had originally. And notice the reason I can take that factor outside the summation is because the p and the k do not depend on the index y. There is another point to make here, in that in the original PMF you have 1 minus p to the power of x. So I just want the 1 minus p to the power of y, and the 1 minus p to the power of k, well, I can actually just take that out the front, right? Because 1 minus p to the k, again, none of these parameters are dependent on the index, so we can just take it out the front, which leaves us just with 1 minus p to the power of y. And now we are starting to see the build-up of something that is looking very similar to the distribution that we want to see. The only thing that we're missing here, you'll notice we've got our x plus r minus 1, which is looking like this y plus k plus r. We've got our p to the r plus k instead of our p to the r. We've got our 1 minus p to the y instead of 1 minus p to the x. We even have our x factorial here. We still have our y factorial. What we don't have, unfortunately, is the very final term, which is the r minus 1 factorial. We do have r minus 1 factorial, but that's not what we want. We want to see instead k plus r minus 1, because that is the new parameter. So let's do that now. Let's go, we've got a 1 minus p to the k over p to the k, close the bracket. Now recall, I'm going to take the k factorial and the r minus 1 factorial out the front. So I'm going to have 1 over k factorial r minus 1 factorial out the front. Again, because they're sort of not useless parameters, but they're not going to help us make this look like a PMF anymore. And I can take them out the front again, because they're independent of the index. We still have the summation y is equal to 0 to infinity of y plus k plus r minus 1 factorial, all over, we've got our y factorial, and we've got our p to the r plus k 1 minus p to the y. We've almost finished this problem. Now remember what I said. Ideally, what do we want in this spot? We want our r minus 1, but what we really want is an r plus k minus 1, because that's our new look distribution. Now, because I've put this in the denominator, I can actually also insert it in the numerator, so theoretically it cancels out and gets us back to the same result. And now we've done what we promised. This whole expression here is starting to look like a PMF. In particular, this second half of the expression, 0 to infinity, is looking like the sum of a probability mass function, where y has a negative binomial distribution, not with parameter r and p, but rather with parameters r plus k and p. So this is just a little bit of a tricky technique here for that second half. We've artificially inserted a lot of parts to this distribution, strategically of course, and we've carefully chosen what we're putting in and what we're taking out as a factor. But all in all, what we've tried to do is get a probability mass function, or something that resembles a probability mass function. Now, of course, we still have the first half of this expression, so still got the 1 minus p to the k all over p to the k. However, do notice that this expression here is actually the definition, the very definition of r plus k minus 1, choose k. And then finally, of course, we know that that 1 minus p to the k over p to the k stays there. The r plus k minus 1, choose k stays. And we know by definition of a probability mass function that the summation across all of the sample space, I should say, all of the sample space of y is just 1. And therefore this expression just looks like 1, and this is our formula here. So, I promised you that we'd get to the mean. So far we haven't got to the mean, but I promise you we're about to in this very next part. Because now, what I can tell you is if we take the expected value of x choose 1, for example, this is going to give you, again, we're going to substitute a value of k equals 1 into the expression. So, in fact, I might just make that a bit more clear. When k equals 1, we have the following. We'd have 1 minus p. Sorry, before I get to that, I just want to explain what this combinatorial factor simplifies to. Well, either one way you can see it as how many ways can you choose one object from x. You can think of it as its very definition. You can do that x times, so you just get x. Or we can use the, the expanded form, and we'd get that becomes x factorial on 1 factorial x minus 1 factorial by definition, which is equal to the expected value of x factorial, the x factorial at the top there can be rewritten as x times x minus 1 factorial. The 1 factorial just becomes 1 times x minus 1 factorial. And then, of course, we've got a nice cancellation of the x minus 1 factorial in the numerator and the denominator. You're just left with x over 1. So this becomes the expected value of x. Now, why did I do all of that? That was just to prove that this is of course the case. This therefore allows us to do the opposite direction and say that the expected value of x is equal to the expected value of x choose 1, which is therefore equal to, if we have a look at our expression, now we can substitute in a value of k equals 1 into this expression here. That gives you 1 minus p to the 1 all over p to the 1 r plus 1 minus 1 choose 1, which is equal to 1 minus p over p times r choose 1. And we know by the very definition of what r choose 1 is, I'm not going to go through a similar example where we had x choose 1 simplified to x. We know that r choose 1 will just simplify to r. And so we're left with r times p minus 1 over p. And there you have it. We've come up with the expected value of x. Let's have a look when k is equal to 2. Now, to derive, let's say, the variance. So, there are going to be a few steps here to derive the variance, because the first step is to derive the variance. We need to derive an expression for the second moment of x. And in fact, to derive the second moment of x, we're going to have to derive a first expression, another expression first. So bear with me as we sort of progress along in this journey. So going back here, when k is equal to 2, what do we have? we have, well, we have firstly the expression of x choose 2, right? We want to have a look at what that comes out to be. That becomes the expected value of x factorial, 2 factorial over x minus 2 factorial over the definition of a combinatorial factor. The first part of, or the numerator here, x factorial, can be written as x minus 1 times x minus 2 factorial, all over, well, 2 factorial is just 2, and we still have our x minus 2 factorial down in the denominator. We notice that the x minus 2 and the x minus 2 factorial at the top can cancel. That leaves us with x times x minus 1 over 2. Now 2 is a constant, and therefore it can be taken outside the expectation. Well, it's really a factor of a half. So it's a half the expected value of x minus 1. And that actually tells us something important or something interesting, because that tells us that if we were to flip this equation around, that x minus 1, the expected value of x times x minus 1, is actually equal to 2 times the expected value of x choose 2. Which in this case, we can now derive using our formula, becomes 2 times. We have our expression for generalized k. Let's take it down, copy that across, paste it in here, and instead of writing k, I'm going to change all of these to 2's. And we're going to change this one, and we'll change this one. So it becomes 1 minus p squared over p squared, r plus 2 minus 1 over 2, or choose 2. This becomes 2 times 1 minus p squared all over p squared. Now, this can be rewritten as simply r plus 1 choose 2. And then again, some extra simplification. We're going to expand the combinatorial factor. That becomes r plus 1 factorial over 2 factorial over r plus 1 minus 2 factorial. Close the, or complete the fraction. Then we've got 2 times 1 minus p all squared over p squared. This r plus 1 factorial is, well, can stay the same for now. R plus 1 factorial over 2 factorial is just 2. And then this expression here down the bottom, r plus 1 minus 2, we can rewrite as r minus 1 factorial. Finish the brackets. We're almost there. 2 times 1 minus p all squared all over p squared. We can rewrite the top factorial as r plus 1 times r minus 1 factorial over 2r minus 1 factorial. And that, of course, allows us to cancel the r minus 1 and the r minus 1 factor on the top. In fact, the 2 and the 2 cancel here. And what we're left with in this expression is 1 minus p all squared, r plus 1, r all over p squared. Phew, still haven't even got close to a variance yet, but I promise you it's coming along, because now we'll be able to derive the second moment of x, and we're going to use this expression here to derive the second moment of x. So note that the expected value of x squared can actually be rewritten as the expected value of x minus 1 plus the expected value of x. And that's of course because if you expand this quadratic term, you get an x times x, which gives you the x squared, minus x. So you get an expected value of x, or minus expected value of x here, cancelling with the expected value of x here. And so you just get left with x squared in this expression, hence why this is true. But now we have an expression for all of these, so let's do it now. Let's find it out. I'm going to just take a copy of what I had here before, take a copy, paste it through. Then I'm going to add our expression for the expected value of x here. This is where it's going to become a little convoluted, but I will try and go through all the steps. First thing I'm going to do is I'm actually going to expand all of these terms. So this would become 1 minus 2p plus p squared, the first term. The second term, when you expand it out, becomes r squared plus r. Now, and then we're still, of course, over p squared. The second component of this, again, remember when we're trying to add fractions, we need to make them on the same denominator. To do that, we're just going to put them both over plus p squared. Now, to go from p to p squared, you need to multiply by p, so we need to do the same by the numerator, so it becomes rp1 minus p. And so far, so good. Now we're going to do a bit more of an expansion. Here we've got our terms here. Now, we're going to have a 1 times an r squared. So we're going to have r squared. A 1 times an r. So we've got plus r. Then a negative 2p times an r squared. Negative 2p r squared. Negative 2p times r, which gives us negative 2pr. Then finally, we've got a p squared times r squared plus p squared r squared, p squared r squared, and finally a p squared r plus p squared r. And then on this side of the fence here, again, I'm going to just expand it. It'll give us an r times p, so plus an rp. And then we're going to have a minus, if you have a look at it here, rp squared. Rp squared, and then of course this will be all over p squared. Now what I'm going to try to do here is combine like terms. The first thing to note is that this plus p squared r will cancel with this minus rp squared, and this plus rp will cancel with one of the minus 2rp's here. So we're just left with minus rp out the front. And so we're going to just have that expression now. We'll rewrite it in a simpler form. That becomes r squared plus r minus 2pr squared minus pr plus p squared r squared. Put that all over brackets, becomes p squared. And so far, so good. Now let's finally derive an expression for the variance. And we know by definition, the variance is equal to the expected value of x squared minus the expected value of x all squared. This, of course, happens to be, well, we can take our expression here that we have at the top, copy this down, paste it down here, take our expression for R1 minus P over P for the definition of expectation. This is going to become, well, the first expression I can just paste for now. The second expression here I'm going to expand, so that will become minus r squared 1 minus p squared. I'm going to distribute the power through the numerator and the denominator, and that's over p squared here. And then a bit more simplification again, I'm just going to have that same factor that I have here. That's not going to change for now, but I am going to expand the other term here. This becomes r squared 1 minus 2p plus p squared all over p squared. And finally, what I'm going to do is I'm going to take this expression, copy it down into the next form, but I am noting now I actually have the same denominator, p squared and p squared here, so I can now add a few more terms to the numerator should I want. And that few more terms will be minus r squared times 1, so we've got a minus r squared. We have a minus r squared times negative 2p. That'll give us plus 2pr squared. And then finally we'll have a minus r squared times p squared, which will give us minus r squared p squared. And what you will notice, very luckily, the r squared here will cancel with the minus r squared here. The minus 2pr squared will cancel with the positive 2pr squared here, and the p squared r squared will cancel with the minus r squared p squared here. And now what we're actually left with is a very simple term, which is equal to r minus pr all over p squared. And then quite simply this becomes in factorial form, or factored out one last time, rp on p squared. And there you have it. We have just come up with an expression for the expected value of x and the variance of x, where x is a negative binomial distribution. The only other thing that I might add to this as an alternative method and a much more simple way to do this exercise is to instead not see x as simply a distribution PMF and brute force through our way through a probability mass function, but rather if we see x, which has a negative binomial distribution, as the sum of independent geometric distributions, in more generally it is the sum of r independent geometric distributions. So I'll write that where xi is IID geometric with parameter p, because you can remember, geometric distributions are for the first failure / success. So now we can see them as this for our particular, or we should say our successes. Therefore, we can write it as the sum of R geometrics, or R geometric random variables. So keeping that in mind, what we can do, in fact, is we could say that the expected value of x is the expected value of x1 plus x2 plus dot 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 plus xr. Now, by the linear or by the properties of expectation, the expectation of a sum is just the sum of the individual expectations, x2 plus dot 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 plus expected value of xr. And if you have a look at a different video, you'll notice that we have derived an expression for the expected value of a geometric random variable. That just happens to be 1 minus p on p. And then the next expression again is the same, 1 minus p on p plus dot 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 plus 1 minus p on p. And of course, how many times have we added that up? R times, because we're summing R geometric random variables. And therefore, we could simply say that is R times 1 minus p over p. Similarly, in a similar fashion, we could say that the variance of x, which is equal to the variance of the sum of x1 plus x2 plus dot 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 plus xr, we could say that is the sum of all the individual variances. Note that this formula is only true, the variance formula that I'm presenting below. The sum of, or the variance of a sum is only the sum of variances when they are independent distributions. So this is not a generic formula. Expectation was generic across all random variables, whether it was independent or not, but this particular formula is not generic. It is only applicable to independent distributions. So keeping that in mind, we note that the variance of a geometric distribution, we've derived that before, is just 1 minus p on p squared, plus, again, 1 minus p on p squared, plus dot 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 dot, plus 1 minus p on p squared. And in case you haven't seen or don't know why that's the case, there is a video on the derivation of this. I encourage you to watch it. And then that gives you, of course, again, similarly, you're summing it across r times. So we've got r1 minus p all over p squared. And there you have it. Very simple methodology in deriving this to be the case, but it was also useful to use it using brute force methods and algebraic manipulation to see the algebra involved, but also appreciate that the alternative method works, and the alternative method gives us sort of a check against our working as well. And of course, for completion, in case anyone was really interested, we can derive an expression for the standard deviation, which is the square root of the variance of x. And plugging that in, we've got r1 minus p on p squared. Or if you really want, we can take the square root function through the fraction, and you can take the square root of r1 minus p all over simply p. There you have it, ladies and gentlemen. We have shown two ways of deriving the expectation of a negative binomial random variable. One using algebraic methods, one using a shortcut rule and recognizing that a negative binomial is the sum of r independent and identically distributed geometric random variables. I hope that this video has been informative for you. Hope to see you in the next one. Thanks.